Okay, these are some notes on section 5.2. Now you should have these 2 pages of PDF notes in the folder, and you can print these out. And these are just some ideas from the textbook that I kind of wrote out for you so you wouldn't have to write them down in your notes. And what we're going to be doing now is we've talked about using LRAM, RRAM, and midpoint RAM to estimate the area under a curve. Now we're going to take this to the next step, and we're going to try to do more and more of these little rectangles. We only did, 6 or 3 rectangles, or, you could do more using, I told you, that RAM program. But the idea is that we're going to be adding more and more of these rectangles. Now, as we add more rectangles, and this is kind of a sketch, this is a general sketch of just one rectangle. As we add more and more of these rectangles, this base of the rectangle, if we have more of these, this is going to get smaller and smaller and smaller. And on the other hand, as this gets smaller and smaller and smaller, we have more and more rectangles in a given interval. So what we're going to do is we're going to decrease these number of rectangles. There's another sketch here I found that we could take a look at, just so you see, have an idea of this. I have to zoom in a little bit on this here. I have to refocus. There you go. And what you can see is if we want to find the area between this curve and the axis, we could use these rectangles, and this would be using 1, 2, 3, 4, 5, 6, 7, 1, 2, 4, 6, 8, 10, 11 rectangles, and 12 maybe if we're going to use a left-hand approximation. And then we could use more rectangles. We could use even more rectangles. All right? And you can see as we add more and more rectangles, we're going to get closer and closer to the exact area. All right? And if these rectangles were just, if the base of these rectangles were just as wide as the diameter of my pencil, this would be all shaded in exactly solid. So, and we couldn't tell the difference. So the more rectangles we add, okay, the better approximation we get for the area under this curve. Now it's still going to be an approximation because we're just adding a finite number of rectangles, but the more rectangles we add, the better the approximation under the curve. So I think you can see that, okay? So you have some rectangles here, more rectangles here, more here, and even more. So as we add more and more and more, we're getting to be more of a solid figure, which is actually the exact area between the curve and the axis. Now we'll talk about this a little bit later, what this represents, because we can't have negative. And remember, if the height of my rectangles will be determined by the value of the function. So here the height is going to have a negative value. All right. Now we don't ever have a negative area, but we can have a negative value. So if we talk about a negative area, it means that the area is under the curve. Positive area is above the curve. Negative area is below the curve. So if we add these all up, we could actually have a number that is not actually this actual area, but what we would call the net area. That's the negative area. And that's the difference between the positive area and the negative area. If I've got more area under the curve, I would have a negative value for this evaluation of all these rectangles based upon the fact that the heights of the rectangle are determined by the value of the function. The function is below the axis here, so this would have negative values. The function is above the axis here, so these would have positive values. And again, these are the heights of the rectangles. The bases of the rectangles are always these little segments here, and these are always positive, okay? So keep that in mind. So we can have positive area and negative area, which is kind of a strange concept, but this is actually a value. We talk about putting all these together. Okay, so hope that makes sense. Now I did kind of give you some notes, but please take a look at the sketches in your textbook, and that's over here. Let me get this back up here. So have your textbook out over on page 274, 275, so you can look at these sketches because these are the same idea. They're talking about the same thing, and these intervals we're talking about. Okay, let me move this here. And so back to your notes. And this is a formalization, and once you see what's going on, it's not too bad. So let's say we want to find the area of this curve from A to B, some point B here, some point A here. A might be x of 0. So we're looking between here and there. Okay, you can see these A and B. So what we're going to do is we're going to make a partition, and it's going to be how we subdivide this interval into little subintervals, and those are going to be the bases of our rectangles. Okay, and we call this a partition. So let P be the partition. A would be equal to x sub 0, and then x sub 1, x sub 2. So it's how we select these values on that interval. Okay, the lengths of the subintervals would be delta x sub 1, so this length would be delta x sub 1, delta x sub 2, etc., etc. And this would be, let's call this in general some interval, we'll call that the kth interval. So this is delta, this is x sub k minus 1, x sub k, so the length of this interval would be delta x sub k. And that's what we have over here all the way to b. And this is the partition of this interval, this closed interval from A to B. And these are how we're going to make our rectangles. Okay, so for our rectangles, the height would be the points. So let's say we pick this particular point, C sub k. Well, it's some point in this interval, into the x sub kth interval, we would call this. And the length of this interval would be delta x sub k. And this is some point. It could be anywhere in here. So for the height of this rectangle, we would actually find the value of the function at that point in the interval C sub k. So that's this point up here would be C sub k, that'd be the x value, and the y value, which is actually the height of my rectangle, the value of the function is f of C sub k. So that's up here. Okay? So the area of this particular rectangle would be delta x sub k times f of C sub k. In other words, that's the base times the height. Okay? And I wrote that over here. That's the area of the rectangle. Base times height times base, I wrote it like this. Height times base, which is f of C sub k times delta x sub k. So that's the area of this rectangle. Okay? And for our rectangles, again, the same thing as what I wrote. Okay? For example, if this is delta x sub 1, then that would be the interval from x sub 0 to x sub 1. That would be the first one. And then C sub 1 would be some point in here. And any point, it would be here. My height would be, in this case, a negative number. Okay? So on each subinterval, we form the product, f of C sub k times x sub k. Now again, this is arbitrary. The product can be positive, negative, or 0, depending on what the value of the function is at that particular C sub k. All right? And if we take the sum of these products, we'll call that sum. We'll use the summation notation. This is going to be the sum of all these rectangles. These are all the heights, and these are all the bases, and that equals the area. The sum, which depends on the partition and the choice of the numbers of k, is called a Riemann sum for the function on the interval AB. That's very important. So that's a Riemann sum. Okay? Hope that makes sense. We'll try to cover one more little portion here. All Riemann sums for a given function. All Riemann sums for a given function. That means we could take all these different ones. It doesn't matter how we break this up, how we partition it. But all Riemann sums for a given function on a closed interval converge to a common value as long as the lengths of the subintervals approach 0. In other words, if these get really, really smaller and smaller and smaller, like we said, we have more and more rectangles because we have a shorter base or smaller base. So as I add more and more of these, as these get smaller, 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 and you can look in your book, they show some examples, or again, we could look at this sketch over here. As these bases get smaller and smaller and smaller, I get more and more rectangles. As I get more and more rectangles, they all approach the same value, which is actually my net area. And that's all we're saying. So all Riemann sums for a given function on the closed interval converge to a common value as long as the lengths of the subintervals approach 0. In other words, I have more smaller bases, so I have more and more rectangles, and eventually I have what we call an infinite number of rectangles. Okay, the longest subinterval is called the norm. That's the biggest, because these don't have to be the same value, and you can look in your book over here, and you'll see over here we have some different length subintervals. Okay, there's one, this is a little bit bigger. Okay, so they're varying lengths, so they don't have to all be the same. Usually we make them the same when we're trying to do computations, but they can be different. But what we do is we call the length of the longest subinterval the norm. Okay, so the longest subinterval is called the norm of the partition, and this will be our partition P. And this is, again, how we break this up, so how we set up these subintervals. So the biggest one of these is going to be called the norm. Okay? And we'll talk about that in just a second, what we do with that.